Welcome to Chapter 5. In this chapter, we're going to start solving systems of linear equations. And we're going to start in section 5.1 with solving systems by graphing. We're going to find out that there's several ways to solve a system, and we're going to go through each technique one at a time. And then the different techniques also work better for different sets of systems. So let's take a look at a warm-up here. The 0.24 lies on which lines below? And so I gave you 3 lines, 2 in slope-intercept form, 1 in standard form. And again, to figure out which lines contain this point or are a solution to the equation, we substitute our x value in for x and our y value in for y. So I'm going to go ahead and do that, pause the video, do that, and then just show this to you so you don't have to watch me do this whole thing. So what I would suggest you do is do these on your own and then start the video again once you get your answers. So as you can see, for each equation, I substitute in 2 in for x and 4 in for y. And then I just went ahead and evaluated each side of the equation. So again, 2 in for x, 4 in for y. So for the first equation A, we end up with a true statement. So yes, this lies on this line. And for the second equation B, we also get a true statement. Half of 2 is 1, 1 plus 3 is 4, and so the y value of 4 matches when x is the input is 2. So it also works for equation B. But if we look at equation C, it does not work. 6 on the left-hand side does not equal 5 on the right-hand side. So the 0.24 is not on this equation. If we were to graph this line in the coordinate plane, the 0.24 would not be on that line. So I want to make a point of the fact that this point lies on both equations A and B. So it is a solution to both equations at the same time. And that's going to be the big idea of what we're trying to get at today. So what is a system of equations? A system of equations is a set of 2 or more linear equations in the same variables. So oftentimes when we see a system, again, usually we have 2, we could have 3 or 4, depending. It gets very complicated, right? The more you get, the more complicated it is. Sometimes we use this bracket notation to kind of put the system together. Sometimes you just see the 2 equations. So here's an example of a system. I'm looking to find when y equals 850x plus 1,000 and y equals 1,100x. And so those are 2 equations that I'm trying to see if there's any common point between them, or I'm trying to see when they might equal each other. And if you remember our Chapter 4 quiz, this represented the cost of the one office building. It was $850 a month with the $1,000 deposit, and the second office building was just $1,100 a month. And so the idea of the same variables is that x and y are representing the same thing here. X is representing the number of months, and y is representing the cost. So when we solve this system, we have if we're in a word problem, x and y are representing the same things. It doesn't make any sense if we're looking for, if x is representing something different in each equation, then that wouldn't be a system because we wouldn't be looking for the same kind of value for x. So what is a solution to the system of linear equations? A solution is an ordered pair that is a solution to each equation in the system. So again, why is it an ordered pair? Well, when we think about lines, right? Lines are a collection of points. And when we think about when the lines would have the same point in common, or when they would share a solution, they would share an ordered pair. So the example here that I want to use is from our warm-up. The fact that 2, 4 is a solution, or is on the lines, is on both y equals negative 2x plus 8 and y equals 1/2 x plus 3. So it is a solution to that system. And again, why is it a solution? Because it makes both of them true at the same time. Let's just do one more together, and then I'll have you do one on your own. Is the point 2, 0 a solution to this system? So to do that, the only way we can do that right now is to substitute again x in for x, y in for y, and see if it's a system to both equations at the same time. So I'm going to take a look at the first one. Is 0 equal to 2 minus 2? Well, 0 equals 0. So 2, 0 is on the first line. Now we got to make sure it's on the second line as well. Y equals negative 3x plus 5. Does 0 equal negative 3 times 2 plus 5? No, it is not a solution to this system. Okay, so it is not a solution to the second equation, so therefore it is not a solution of the system. Because it doesn't satisfy both equations at the same time. It satisfies one, but not the second. So what I want you to do is go ahead and pause the video and try example 2. I have a new system for you and a new set of ordered pairs, and then you can unpause the video and see my work when you're done. So as you can see, in this example, yes, 1, 3 is a solution to the system because when we substitute x is 1 and y is 3 into both equations, we end up with a true statement in both equations. So yes, it is a solution to the system. It makes both equations true. So when we look at solving a system, so far I've just given you a solution and I'm giving you a point and I'm asking you, is it a solution? But now what we want to do is be able to solve the system ourselves. So I'm going to actually toggle to the version that has a graph. One of the ways we can solve a system is by graphing. And this is kind of what I wanted to get at before, but I didn't want to introduce it too soon in the lesson. What's going to happen is we want to see where the lines intersect. That's going to represent the solution, because if we have one line, right, and we're looking for, and all these points are solution, and then we have a second line and all these points are solutions, this point here, the point of intersection, is going to be the solution for both lines at the same time. So again, we're looking for a point that works for both equations at the same time. So this is where we need our graphing techniques that we learned in chapter 3. And I'll do the graphs in different colors. So for this first problem, both of these equations are in slope-intercept form. Our y-intercept is 8 for the first equation, and our slope is negative 2. And recall that means negative 2 over 1. So we're going to go down 2, right 1, down 2, right 1. And that is not a great line. Let me try that one more time. Remember, when I try to do these on my computer, it doesn't like when I go down like this. Okay. You will have a ruler, or you should have a ruler, or some sort of straight edge. It's going to give you a better line. The second graph, y equals 1/2 x plus 3. Our y-intercept is 3, and our slope is 1/2. So we're going to go up 1 and right 2. Can you see where the point's going to be? Up 1 and right 2. And that is this graph, this line. And so as we can see, the point 2, 4 is a solution to both systems. Now, I specifically chose this example because that's right, you guessed it. It's the same problems from our warm-up. So we checked the point 2, 4. It worked in both lines algebraically. And then graphically, when we look at the equation, they both have the same point of intersection. I have that intersection point at 2, 4. So you can check your answers, of course, by, again, back substituting 2 and 4 into the equation, but we already did that in the warm-up. For problem number 2, we will do the check. So what I like about problem number 2 is one of the lines is written in standard form. And one of the ways we can graph a line in standard form is to use the x and y intercepts. So the x-intercept, remember, is when the y is 0. So 0 plus x equals 3, which means x is 3. Sometimes you have to do some more solving. So I'm going to graph the point x equals 3. And then for the y-intercept, it would be y plus 0 equals 3. When the x is 0, y equals 3. And so I'm going to graph that point on the y-axis. So this particular line, I graphed using the intercepts. The second line here is in slope-intercept form, where my y-intercept is 5 and my slope is 1. Remember, this coefficient here is 1. So I go up 1, right 1, up 1, right 1. And if I graph this, all right, so this is a little trickier. It's not going to be right on a perfect point of intersection. It looks like it's -0.5 and then 3.5. Okay, sorry everyone, I made a mistake there. Let's back up. I put my y-intercept at the wrong spot. I did check this and it did not work. I paused the video and checked it. Okay, let's go back. Apologies there. Okay, my y-intercept is 5, not 4, and I go up 1, right 1. Now, if you notice, I'm like running out of graph, so I can actually go down 1 and left 1. Remember, -1 over -1 is the same thing as +1 over +1. Okay, this is a lot better. It's not that you can't have an intersection point at the halves. It's that normally when we introduce something like this, it's going to be nice integer coordinates. Okay, this makes a lot more sense. So our point of intersection is -1, 4. Let's go ahead and check that. So in our first equation is 4 plus -1. Remember, y is 4, x is -1, equal to 3. Yes. And our second equation, which is y equals x plus 5, is 4, which is our y, equal to -1 plus 5, which is our x. And yes, it is. So as you can see, that point lies on both equations at the same time. What I'd like you to do is try number 3 on your own, and then you can unpause the video and watch what I do. So there are a couple ways to graph these equations. For number 3, the first one, both of these equations, are in standard form. The first equation, it's actually easy to find the intercepts because the intercepts are going to be integer values. So when y is 0, x would be 8. When x is 0, 2y would be 8 or y would be 4. The problem is, if you notice, I don't have 8 out here on my my x-axis. So instead, I'm going to put these lines into slope-intercept form. So if we have x plus 2y is 8, I'm going to go ahead and subtract x. Remember, I want to isolate y. So 2y equals, I'm going to make this -1x plus 8. And then I'm going to divide by 2. And my equation in slope-intercept form is y equals 1/2 x plus 4. So I'm going to go ahead, I'm going to double check there. There we go. 4 is my y-intercept, down 1, right 2. And there we go. Again, it doesn't like when I try to graph that. Oh, so wiggly. My second equation, let's use orange. This one, I would definitely put in slope-intercept form because if we go to solve for our x-intercept, imagine we didn't have this y here. 3x equals 8, that is not an integer value. And anytime you go to graph intercepts, if you're looking at decimal or fractional values, you're not going to get an accurate graph. And the more accurate our graph is, obviously, the more accurate our solution is going to be by graph. So again, I'm going to go ahead and make this into slope-intercept form. I'm going to subtract 3x. That gives me -2y is -3x plus 8. And then I'm going to divide by -2. And a negative divided by a negative is a positive. 8 divided by -2 is -4. So my slope-intercept form here is y is 3/2 x minus 4. So my y-intercept is -4. My slope is 3, so I rise 3, run 2, rise 3, run 2. And there it is.